Okay, ready to dive into some seriously strange science? We're tackling quantum electrodynamics today, QED for those in the know. And we've got Feynman's book, QED, The Strange Theory of Light and Matter, right here to guide us.
Feynman himself called this stuff absurd, and he wasn't one to exaggerate.
Right. And that's why I'm kind of nervous, but mostly excited. This isn't about turning us into quantum physicists overnight, is it? It's more like trying to understand how the universe works on a deeper level.
Exactly. It's about peeking behind the curtain of reality, seeing the machinery, the strange machinery that makes it all tick.
And QED, this is our best look at that machinery so
Well,
far.
without a doubt, it's given us the most accurate description of the universe we have. But it comes with a catch.
Oh, I figured there had to be a catch.
It completely upends our everyday intuition. Our common sense goes right out the window.
Okay, so maybe I should buckle up. So where do we even start? With the absurdity that is light acting like both a wave and a particle. It's like it can't make up its mind.
Yeah, it's like, pick a lane, light. Are you a wave or a particle? It drove physicists crazy for centuries. They even had this joke. Light's a wave on Mondays, Wednesdays, and Fridays.
And a particle on Tuesday, Thursday, Saturdays.
You got it. I guess Sunday was a day of rest for the poor photons.
Uh-huh, right. So how did QED finally solve this whole wave-particle mess?
By saying, you know what? Forget the wave part. Light us particles.
Photons, right.
Yeah, photons. But, and it's a big but, we had to give something up to get there. We had to let go of certainty.
Certainty, like we can't be sure what light is anymore.
Not exactly. We can be sure it's made of photons. But we can't predict with absolute certainty what any individual photon is going to do. Instead of saying, this will happen, we have to talk in terms of probabilities. This has a certain chance of happening.
Okay, so that's where things start to get a little fuzzy, right? This whole probability thing. And how do you even calculate those probabilities? Are we talking insanely complicated equations here?
Oh, the equations can get pretty hairy, yeah.
Mm-hmm.
But Feynman, he came up with a more intuitive way to think about it. He used arrows.
Arrows. Wait, what? Like arrows I drew back in high school physics to show which way a ball was going to fly.
Sort of. They represent the probability of something happening. It's a visual representation of the math. The longer the arrow, the higher the probability.
So a short arrow means something's unlikely to happen.
Exactly. Like the universe is playing darts, and a short arrow means it's probably going to miss the target.
Okay, that makes sense. But how do you figure out the overall probability when there are multiple possibilities? Do you, like, add up all the arrows?
That's where things get really wild. You don't just add like you'd add numbers. Instead, you
Oh.
have to combine their lengths and directions.
Combine their, what? How do you even combine arrows? That sounds messy.
It's like, imagine instead of adding your money together, you combine the strength and direction of your pushes on something heavy.
Wait, what? Like, if me and you were trying to push a car?
Yeah, you wouldn't just add your strength together. You'd have to factor in whether you're both pushing the same way or in opposite directions.
Okay, that actually makes sense.
Yeah.
But it still feels weird to think about it with probabilities instead of pushing.
And that's QED in a nutshell. It's counterintuitive. It forces us to rethink how we view the world on the smallest level.
I'm starting to see why Feynman called it absurd. We've got light acting like it has a multiple personality disorder. Probabilities as arrows.
And we're just getting started.
My brain's already doing backflips trying to picture probabilities as arrows.
Yeah.
But we've only been talking about photons so far, right? Those little packets of light. What about electrons? Those tiny guys whizzing around the nucleus, like miniature planets, right?
Well, the miniature planet idea, that's a good starting point. But in the quantum world, things are always a little weirder than they seem.
Oh, I'm picking up on that theme for sure.
Mm.
So what makes electrons so special in the QED universe?
For one, they're also governed by these arrow probabilities, just like photons. But here's the real kicker. Electrons are the ultimate introverts. No two electrons can ever be in the exact same state at the same time.
Wait, seriously? They're like, nope, get your own quantum space, buddy.
It's called the exclusion principle, and it's one of the most fundamental rules in quantum mechanics. Each electron needs its own unique quantum address, and they guard those addresses jealously.
Okay, so electrons need their space. But how does that affect, well, anything? We're not all just giant clouds of unorganized electrons, right?
Exactly, and that's the beauty of the exclusion principle. Without it, all those electrons would just clump together in the lowest energy state possible. No structure, no variety, just one big, boring blob of matter.
Hold on. You're saying this no two electrons in the same state rule is the reason we have stuff? Like the reason I'm not just a formless puddle of particles.
You got it. It's the foundation of chemistry, the periodic table, everything we see and touch around us. It's because those electrons need their personal space that atoms bond the way they do, creating the incredible diversity of molecules and materials that make up our universe. Think about it, without the exclusion principle, there'd be no you, no me, no deep dives into the strange world of QED.
Whoa, that's heavy, man. Literally. So we've got these arrow probabilities governing how photons move and interact. We've got electrons with their strict no trespassing signs shaping the material world. And somehow, this crazy system actually works to create the universe we know and love.
And here's the amazing part. QED describes all of these interactions with incredible accuracy, using just a handful of basic rules. It's like the universe is playing a cosmic game with incredibly simple rules, but the complexity comes from how those rules are combined and played out on such a vast scale.
Okay, now I'm even more curious about these rules. How few are we talking here? Give me the QED rulebook.
You ready? There are really only 3 fundamental actions that govern everything QED describes.
3. Only 3. That seems way too simple for something as mind-blowing as quantum electrodynamics.
I know, right? But it's true. And the first one is about as straightforward as it gets. A photon goes from point A to point B. It's just light traveling through space, something we're all familiar with.
Right, light's always on the move.
Yeah.
What's next on our QED rule list?
Number 2, an electron goes from point A to point B. Just like photons, electrons can't seem to sit still. They're constantly zipping and zooming around within atoms and between them.
Okay, those first two make sense. But where's the interaction part? How do light and matter actually, do stuff together?
That's where our third and final action comes in. An electron emits or absorbs a photon.
So it's like a game of quantum catch. Electrons tossing photons back and forth.
That's a pretty good analogy. And each of these actions, every photon moving, every electron jumping around, every emission or absorption, each one gets its own little arrow, its own probability amplitude.
So let me get this straight. These 3 ridiculously simple actions, governed by those weird arrow probabilities, they're the basis for pretty much everything we see around us.
Well, almost everything. QED has been incredibly successful at explaining the interactions of light and electrons, and those interactions really are the foundation for so much of what we observe in the universe.
Almost, you say. Are you about to hit me with some limitations of QED? Because my brain is just starting to wrap itself around all this.
Well, QED does have its boundaries. It's an incredibly powerful theory, but it doesn't explain everything.
Okay, gotta ask, what doesn't it explain? Don't tell me it's all just a simulation or something.
Haha, not quite. But we've been focusing on electrons and photons, right? They're those other particles hanging out in the nucleus, protons and neutrons.
I know those guys. They always seem kind of mysterious. What's QED got to say about them?
Well, they're not so easily explained by QED. It's like trying to use a map of the city to navigate a whole different country.
A different country? How so?
Protons and neutrons, they're not fundamental particles in the same way that electrons and photons are. They're actually made up of even weirder things called quarks, held together by gluons. And those guys, they play by a whole different set of rules.
Okay, things just got way more complicated. Quarks, gluons, it's like there's a whole deeper level to the quantum world that QED just doesn't address.
Exactly. It's like QED gave us an amazing user manual for building a car, but when you pop open the hood, there's a whole other engine down there running on different principles.
So we've got the electromagnetic force that QED describes so well, governing how electrons and photons interact. But those quarks and gluons, they're playing by the rules of the strong nuclear force, right?
You got it. And the strong force is, well, strong. It's what binds those quarks together to form protons and neutrons, and ultimately it's what holds the nucleus of every atom together.
Okay, so even though QED is mind-blowingly accurate, it's really just one piece of a much larger, more complex puzzle. It's like we've illuminated one corner of the universe, but the rest is still shrouded in darkness.
That's a great way to put it. And it's not just the strong force that QED doesn't quite cover. There's another big one: gravity.
Gravity, you mean the thing that keeps my feet on the ground, that keeps the Earth orbiting the sun?
The one and only. We've got Einstein's general relativity for describing gravity on those large scales, planets, stars, galaxies. It worked beautifully. But a good quantum theory of gravity, that's the holy grail of modern physics.
So we've got QED nailing the electromagnetic force, but gravity is still this big question mark.
Pretty much. It's like trying to fit a square peg into a round hole. We've got 2 incredibly successful theories: quantum mechanics, which QED is a part of, and general relativity, but they don't quite play well together.
But that's a lot to wrap our heads around. QED is this amazingly accurate theory, but it's clear there's still so much we don't know. It's kind of humbling, isn't it?
It really is. But that's the beauty of science, right? The more we learn, the more we realize how much there is still to discover. And who knows what incredible breakthroughs await us in the future. Maybe one day we'll crack the code of quantum gravity or uncover even deeper layers of reality that we can't even imagine right now.
It's both exciting and a little terrifying to think about, isn't it?
Yeah.
But hey, that's the universe for you. Well, folks, we've journeyed into the heart of quantum electrodynamics, explored its bizarre logic, and glimpsed its incredible power. We've learned that light can be both a wave and a particle, that electrons have a serious aversion to sharing space, and that probabilities are best represented by arrows, of all things.
And we've only scratched the surface. If you're itching to dive even deeper into this mind-boggling world, I highly recommend checking out Feynman's QED, The Strange Theory of Light and Matter. It's a wild ride, but trust me, your brain will thank you.
Absolutely. So until next time, keep those minds curious, and remember, the universe is stranger than you can imagine.